So let's just go ahead and get started here. So our first question is, what is the wavelength of light that has a frequency of 4.2 times 10 to the 18th hertz? What type of light is this? Okay, so we start with our 4.2 times 10 to the 18 hertz. Now remember, our equation here is C equals lambda V times V. Okay, where C, this is the speed of light. Okay, our lambda there is the wavelength, and V is the frequency of the light. Okay, now we can algebraically rearrange this to get what we need. Okay, remember we need wavelength out of this. So C equals lambda V. If we divide both sides by V, for the algebra there, to satisfy algebra, the V's cancel, and we get C over V equals lambda. So let's go ahead and plug our numbers in. Okay, we've got, remember speed of light is 3.0 times 10 to the 8th meters per second. And that is divided by our V, which is given to us in the problem, of 4.2 times 10 to the 18th hertz. Okay, now remember hertz is equal to 1 over a second, or a cycle per second. So let's go ahead and put this into our calculator. All right, 3.0 times, or 10 to the 8th, divided by 4.2 times 10 to the 18th. And that ends up equaling 7.14 times 10 to the negative 11th. So 7.14 times 10 to the negative 11th. Okay, so let's talk about our unit here. For speed of light, we got meters over seconds. We're going to divide that by hertz, which is 1 over a second. Well, we've got to, flip the, if we're dividing by a fraction, we flip it, we do the reciprocal. So we've got meters per seconds times seconds over 1. The seconds cancel. We're left with meters as our unit for this problem here. So our final answer is 7.14 times 10 to the negative 11th meters. Okay, so for our second type of problem, we've got what is the frequency of light with a wavelength of 650 nanometers? So we're going to use the same equation, C equals lambda V. Okay, but that 650 nanometers gives us problems, okay, because speed of light is in meters per second. Nanometers, okay, speed of light, meters per second. Nanometers, not the same unit, so we need to convert that using dimensional analysis. So we start with our 650 nanometers. Okay, in 1 meter, which is our larger unit there, what we're wanting to get to, we have 1 times 10 to the 9th nanometers. Okay, so our calculator there, we've got 650 divided by 1 times 10 to the 9th equals 6.5 times 10 to the 7th, negative 7th. 6.5 times 10 to the negative 7th. Okay, and our unit for that would be meters, which is what we were wanting to get it to. So now that we've got the actual wavelength, okay, in the correct unit, we can calculate the frequency. So once again, we'll do some algebraic rearrangement of our problem there, this time dividing by lambda on both sides. So we get frequency isolated. Okay, and what we get is C over lambda equals V. Okay, so let's plug our numbers in. We've got 3.0 times 10 to the 8th meters per second over lambda, which we calculated earlier, of 6.5 times 10 to the negative 7th. And that's in meters. Okay, so if we're thinking our unit cancellation, the meters cancel out there. So let's go ahead and run this through our calculator as well. Okay, so 3.0 times 10 to the 8th divided by 6.5 times 10 to the negative 7th. And that equals 4.61 times 10 to the 14th. So 4.6 times 10 to the 14th. Let's just leave the 1 off. Okay, now what is our unit here? Meter? Oh, nope. It's not meters. That's not what we wanted. We actually want it in reciprocal seconds or hertz. Okay, remember 1 over a second is the same as hertz. So that's our second type of problem. Okay, let's move on to our next one. Now this one we're going to use a different equation for. The other equation that we've learned about here, okay, so it's what is the energy of light with a frequency of 2.2 times 10 to the 8th hertz. So our equation here is energy, which is symbolized by E, is equal to H times V. Now V is the same as it was last time, so that's still frequency. Now the H is Planck's constant. Now Planck's constant is just a number. You do not necessarily need to remember it. It will be given to you on test. But Planck's constant is 6.626 times 10 to the negative 34th joule seconds. Okay? And that's the constant. You need to memorize that, or you do not need to memorize that, sorry. Okay, so let's plug it into our equation. Okay, we're given frequency, we've got Planck's constant, we need to calculate energy. So energy is equal to Planck's constant, 6.626 times 10 to the negative 34th, times our frequency given, 2.2 times 10 to the 8th. Okay, so we get our calculator. Our calculator, need to move it there just a little bit. So 6.626 times 10 to the negative 34th times 2.2 times 10 to the 8th. And that'll equal 1.4546 times 10 to the negative 25th. Okay? Energy equals 1.45 times 10 to the negative 25th. And this is energy, so our unit here is joules. Okay? If we want to think about our unit conversion here, we had joule seconds times 1 over a second. The seconds cancel, and we're left with just joules. Okay. So, moving on to our last type of problem. Question is, what is the energy of light with a wavelength of 4.3 times 10 to the 12th meters? Okay, so we want to find energy, but we're given wavelength to begin with. So that means we're going to use two equations. The first equation is C equals lambda V, and then we're going to use the second equation, E equals H times V, Planck's constant times frequency. Okay, we're starting with the wavelength. We want to get, okay, that's what we're given. We want to get to energy. So we're going to use our first equation first. Okay, now we're going to start with V. That's what we were starting with wavelength. We want to get V so we can then plug that V there into our second equation. Okay, the first equation, the V in the first equation leads to us solving energy in the second equation. So remember when we did earlier, C divided by lambda equals V, which is what we want to find to start off with. So 3.0 times 10 to the 8th meters per second over our wavelength of 4.3 times 10 to the 12th. That gives us our frequency. So calculator out. Let's move it just a little bit there. We've got 3.0 times 10 to the 8th divided by 4.3 times 10 to the 12th. And that ends up equaling 6.98. 6.98 times 10 to the negative 5th. Okay, and that would be in hertz. That's our unit. So we take that hertz that we just found, that frequency we just found, and we plug it now into our second equation so we can find energy. Energy equals Planck's constant, 6.626, times 10 to the negative 34th, times what we just found, the 6.98 times 10 to the negative fifth. Okay, so put our calculator, let's move that calculator there. For some reason it's not moving. Okay, there we go. There we go. That was kind of embarrassing. Alright, so 6.626 times 10 to the negative 34th. There we go. Times 6.98 times 10 to the negative fifth. That equals 4.62 times 10 to the negative 38th. So equals 4.62 times 10 to the negative 38th, and this would be joules. Okay, our unit here is joules. Alright, so that basically goes over the main types of problems dealing with energy. If you have any questions at any time, just let me know. Okay, have a good one. Catch you later.